Hello, friends of reinforcement learning for large language models. What if I told you that I had a procedure that could make reward go up? Doesn't require any extra data or anything external at all. It just makes reward go up. Now, if this sounds too good to be true, I have to say it's only a little too good to be true. And we'll see what that little is, but it surprisingly seems to work. So this is a paper called Reinforced Self-Training, or short REST, for language modeling. The main authors are Kaglar-Gulchere, Tom Lepin, or Lepane, I'm sorry, Tom, and Srivatsan Srinivasan. And it is by a conglomeration of Google and DeepMind, or Google DeepMind. Not exactly sure which of the organizations have existed or exists at the point in time where this paper was written, although it is a fairly new paper, but it sort of comes from the deep Google corner. This paper, as I said, it has a procedure that fully relies on the trained model that you get out of training, out of regular log likelihood training out of a language model. And it's a procedure to just somehow make reward go up by self-bootstrapping. So by producing your own data and then training on that produced data. Now, as I said, we'll get into the extra bit that's kind of necessary here that's not super much spoken about in the paper itself. They themselves say reinforcement learning from human feedback, or RLHF, can improve the quality of large language models LLM outputs by aligning them with human preferences. So they're in the domain of learning from human feedback, like taking a language model, taking labeled training data that humans have annotated or humans have demonstrated somehow. So humans have taken some kind of text input and have demonstrated how to do whatever task. In this paper, that's translation. So we have a data set that, for example, has German sentences in it, and we have the corresponding English sentences done by professional human translators. So from this data set, this is a task where you could apply RLHF or a setting, let's say. But you could also just train the model. We'll get into all of these things at the moment, because reinforcement learning is a term that kind of gets stretched in the meantime. They say we propose a simple algorithm for aligning LLMs with human preferences inspired by growing batch reinforcement learning, which we call reinforced self-training. Given an initial LLM policy, REST produces a dataset by generating samples from the policy, which are then used to improve the LLM policy using offline RL algorithms. They say it's more efficient than typical online RLHF methods because the training dataset is produced offline, and so on. So this is, as I said, a procedure where you generate your own data. Now, the entire abstract and the paper in themselves, they don't exactly mention, as I said, the core ingredient, which is going to be the reward model that goes into here. And we'll see the entire procedure. So we'll dive in. We'll go a little bit into language model training. We'll go a little bit into reinforcement learning as such and the combination of the two, and what exactly makes this paper work. And also we'll go a little bit into what I think is maybe like the secret working horse behind the whole method, or at least behind a part of it, and something that might actually be an alternative reason of why this method works better than, let's say, RLHF in an online fashion. Also, you'll notice the return of the mirrored glasses instead of the dark black glasses. There's actually a funny story behind why I have these now, and that story is I can't find the other glasses. So there's that. Now bear with me as we go through this paper. So let's say you have just trained your very own language model, and you've done so on a data set. And that data set, as we said, is translation, or it has samples from translation. So let's say we have data X and corresponding labels Y. And we have kind of lots of them, X, Y, X to Y. On that data set, we can train a translation model. So a translation model that takes in some X So the model takes in some x and gives me a corresponding y hat, like what it thinks the output should be. Now the question is, how can we use this model here to improve itself? Well, what we could do is we could simply take this x and this y right here and say, well, that's kind of a new data point. Since these are in a translation model with a stochastic output that we sample from, they're quite unlikely to be the exact. So let's say that this x is exactly this x. We take it from the data set right here. They're quite unlikely to be the exact same output. So we'll say, well, this is kind of like a new data point. So can't we make a second data set, add this right here, so the same x, but in this case we'll pair it with the y hat. And so let's say this is x1, x2, x3, so x1, y hat 1, x2, y hat 2. So we'll just let the model infer. We can even do that multiple times, right? So for x2 we can produce another, so y hat 2, another inference, and we'll make like ourselves a new data set, and then we can just take them together and kind of train the model further to get a new model, right? Now, what's the problem? The problem with this is kind of you're eating your own poop. Right? So if the model is good, it's going to produce good data, but it's only like the data it's going to produce, if I train on it in expectation, I shouldn't see an improvement, right? Because the data is, let's say, this good. So if I train on data that's this good, I should get a model that's this good again. So naturally, this will somehow stabilize to the performance that the model is already at. So this by itself doesn't work. I can't just produce data and then train on it, although someone should maybe try that. Actually, they do try it in the paper and it improves, which I find very suspicious. But let's just assume in a normal, reasonable world, this does not work. You can't just produce data and then train on that data. So what do? Well, how about we somehow figure out which of these translations are good and which are bad, right? So somehow we figure out, oh no, this one is really bad and this one is good too. And by the way, in the original data set, that one here is also not as good, right? So we just kind of have a method to strike out the bad data, which gives us only good data. And since we can produce more data, we can even keep the volume of data constant as we just cull down on the bad data, or we can even increase the volume of the data, so how many data points we have. And then that data set naturally has a better quality because we just filter out all the bad examples. And with that better quality data set, we can then go train the next model, which naturally, since it's trained on better data, will be of higher quality. And again, we can use that next higher quality model to produce data. Since that model is now higher quality, the data is already likely to be of higher quality. We can again use our filtering procedure and we can create an even better data set. This has been done in recent times quite a number of times, like a lot of these automated instruction tuning data sets are done like this, but that kind of relies on an external thing. So you go to GPT-4 and you tell GPT-4, make me a data set. And then you go to GPT-4 and say, well, make me a harder data set, right? And a harder data set. But that relies on GPT-4 being this really good model that you can sort of suckle the quality from by getting data from it. However, this here, we just produce data from the model that we've trained. So you'll naturally see that this can only work if our filtering procedure that we apply over here and here is somehow better than, is somehow good. So if that filtering procedure is good, then we can use it to create ever better data. If that filtering procedure is bad, then it will not give us an improvement. So that's the kind of missing piece in this paper that they don't speak about too much, which is they need a reward model to assess whether any given created data point is good or bad. And that reward model, they don't even say whether they train their own. They just say kind of from what it's called metric X. Now, I don't know if that's a trained, like if they take the actual reward model from some other paper, or if they just take the architecture, like the methodology, and somehow train on their own data or create the reward model from their own data. I don't know. I don't actually even know if it's a trained reward model or if it's like a heuristic score like Blur. So they don't specify that too well, and it is the driving horse behind this whole methodology. So I do believe that should be highlighted a bit more. But you can see right here what they do. So they do essentially what I said, but in a bit more intricate fashion. So given a language model, and as I said, this all starts out with an already trained model. That's kind of step one, is I train a model and on some kind of task, in this case translations, so going from German to English. And then I have version 0 of that model. So the first thing I do is I go through what they call a grow step. In the grow step is where I make this new data set. So I simply take the old data set, specifically I take the X values of the old data set, I run them through the model, and the model produces these estimated outputs, right? It just runs inference over that, and I create this new data set right here. So this original data set they call D, and then the combined data set they call, I believe, DG. Yeah. So this by now is simply a bigger data set that is augmented by the generations of the model itself. Does nothing yet. It's just a bigger data set with some synthetic data. Then they go into this improve step. So in the improve step, they do two things. First, they filter that data set, and that's the green procedure right here. So DG becomes sort of filtered DG. Now, I don't know exactly how to, let's say, modulo the filter. And the filter is simply the reward function that you get from somewhere. So just imagine you have some kind of reward function that can assess really well if a translation from German to English is correct or not. You just annotate with that reward model all the data, and then you just filter. You set some kind of threshold, and you say, well, everything lower reward than that, I don't want in my data set. I just want the higher data set. So you take that DG, you filter it down so you only have good data, and then you train the model on that. And you can see that there's an inner loop right here. So the inner loop can be executed multiple times. That means if I have my new data set, let's redraw this DG, no, just DG, that new data set is kind of, this is all of my data, and let's assume it's sorted in this way by the reward. So things on higher up, they have higher reward. So the first iteration might be I go and I just filter from here. So everything above will be in my data set for training. But then I do a second step with the exact same data set. So I can reuse that data. I'll just filter it down to higher quality. So I retain less of it, but what I retain has higher quality. And I can do that multiple times. So I can reuse that same data multiple times, zip, until I just remain with the highest quality data. So this can be an inner loop on the exact same data set. So the thing that these authors mostly optimize is how often do I have to generate a new data set, because they say that's the actual slow part in all of these sort of self-training and reinforcement learning procedure. So let's, so this would be the inner loop, right? And the outer loop would then be, so I have here, I've trained a model here. So I've M0, model 0. I train M11, M12, M13. So all of these build upon each other. And then I use M13 to create an entire new data set, which will become sort of a bigger data set. So I join the original data set and I can join it with this new one from the first step and with the new one from the second step. So I use that to create this, and this I can then reuse multiple times. So the inner loop is simply to reuse the produced data multiple times simply by consecutively filtering them down. Let's contrast this with true online reinforcement learning from human feedback. So the RLHF that's currently popular is using an algorithm called PPO, proximal policy optimization. Now, this is an algorithm that is quite a basic reinforcement learning algorithm, and it has some kind of a built-in regularization, which is this proximal part right here. We won't look extremely much into this, but essentially in reinforcement learning, you have the agent and you have the environment, right? The agent gets an observation from the environment and it sends back an action, and it then gets a reward, and then it starts all over again. Now, in language model reinforcement learning, we don't have a loop actually. So there's only one observation, there's one action given, and then there's one reward, and then it's over, and then we take the next sample. So every data sample is an entirely new episode for this. So speaking of reinforcement learning in these things is due to how we do the loss, and not necessarily that it's reinforcement learning like it's AlphaGo and you need to plan multiple steps ahead and yada yada yada. So I guess no, you could probably view each token as an action, but you still get the reward at the very end. But so in any case, in language model, so the agent would be our large language model, or in this case, you also sometimes, so pi would be the policy. All of these things you can just interchange them. The agent in reinforcement learning has a policy, but we mostly use them interchangeably. The LLM is technically that policy. So sampling from the LLM would be the agent's policy, or assessing the likelihood of something. The observation here would be our X. So that would be the German sentence. So that goes into the LLM. The action would be the Y hat. So whatever we sample from the language model. So the English sentence that it thinks is the translation. And then the reward is given by the reward model. So we call that capital R. It takes in X, it takes in Y hat, and optionally it could take in the label, the reference, but that's only in this case of translation. Scores like Blur, so they take in reference translations and they see how well the given translation matches with that reference translation. But it could just be a trained reward model that doesn't need the original label right here and can just assess somehow. So if you look at papers like Instruct GPT, or so, what they do is first they collect human feedback to train that initial model, M0, right? And they do that with regular language modeling loss. In this paper, they also call this behavior cloning. So behavior cloning or language modeling, or all of this is essentially the same. And they write that down here in a formula. Here, somewhere. Did that paper recently change? No, here it is. So they write it down in this formula right here. Here is the lot. So here is how it comes to be. They simply say, this is reinforcement learning math for language modeling. So if I have a German sentence and I want to make an English sentence out of it, this here is my policy, then essentially this is the multiplication operator. That's kind of like my likelihood or my distribution of each token given the previous tokens and the input sentence. So this is the way for writing the policy for stepwise autoregressive sampling, right? Each token depends on the previous tokens and on the input. Therefore, if I have training data, that's crazy. That's the D right here. So I have xi, yi pairs, right? And xi comes from some kind of a base distribution, and yi comes from the true distribution of translated sentences. So human expert translations. I can define my log loss as such. So given that I do the log, this becomes the sum, not the multiplication. But essentially, you'll see here, this is simply the language modeling loss. So it's an expectation over my data set. I input X, and I simply say the next token, how likely is it given the previous tokens and X? So this is teacher-forced language modeling. What I do in practice is this here is a big transformer network, or in this paper, a smaller transformer network. That transformer network will output some sort of a distribution, like distribution, softmax distribution over its vocabulary. One of them is going to be that true token right here. Let's say that's going to be this one here. And I do my softmax loss, I forgot what it's called. Cross entropy, sorry. My cross entropy loss between the true distribution, which is just the Dirac, essentially the 1 here and 0 everywhere else, and the output of the language model. So this is called log likelihood loss. It's called behavior cloning. All of this is essentially I train my language model on a given data set of input-output pairs. So this would be also what Instruct GPT does in step 0, where they simply say, it's also called supervised fine-tuning, all these names. So we supervised fine-tune a language model on a given set of human annotated data. From that, right, from that we go into this loop. Now, if we were to go on, like, for example, Instruct GPT or other reinforcement learning from human feedback papers, the second point would be to somehow create a reward model. And there are different ways, and I'll leave it away exactly for here how you create this reward model. Some do it by collecting more human data, right, on the model outputs and so on, but you somehow collect a reward model, and then what you do is you take data, X, input data, you output Y, but instead of now comparing it in a token by token softmax cross entropy way to the original reference output by the humans, you simply take the reward model and have it give you one number at the end. The difference is you don't get a number per token, you just get one number. Like in behavior cloning, you get a number and you get which token is the correct one. Here you don't get any of that. You simply get a number. Okay, so the challenge in reinforcement learning is, okay, I now have to, from that number, learn to do more or less of what I just did, the entire sampling sequence. And as you can imagine, that takes a lot of samples. So because I get way less information, I just get one number per episode, I have to use more samples to get there. And the problem is that inferring this y hat right here from the LLM in this online fashion is timely. So every time I want to collect a reward, I actually actively have to run language model inference to get that reward, to get the training. And they say, well, this is inefficient. What if we could generate the data once offline and then just reuse the data multiple times? So we generate it once using the model. That's the exact same thing as here, right? We generate data using the model. But then instead of only using that in the moment once with the reward model, in this way we can reuse it multiple times. And isn't that fantastic? Now there are more differences. As I said, here we train with the reward, and here we filter we filter by the reward model and then train simply with the regular language modeling loss. But that's essentially the difference to the online reinforcement learning. So we can see this paper in, so there's an algorithm, there's a graphic explanation. So this is the graphic explanation, and the graphic explanation essentially says, I start with the grow step, and after the grow step, I have my data distribution, right? Which is maybe like this. That's my data distribution in the reward. That curve is exactly replicated over here. Now, what I'll do is I'll simply filter by the reward model and say, okay, everything up here is now my new data. And in the second step, I take the same data and say everything up here is now my new data, and so on. Everything up here is now my new data. You can see data gets smaller, but quality of data gets higher. Again, this is fully reliant on me having some good reward model, which they are very, very vague about where it comes from. So here they say, well, our implied distribution here shifts and shifts and shifts, and I can take the last model from here that I trained on the super good data, and I can grow my data set again so that I don't keep shrinking my data. I can actually produce more data. So their conclusion is going to be that more than 2 growth steps are probably not worth it, because again, you're sort of still eating your own poop. Even if you filter that poop by quality of poop, you're kind of still eating your own poop, and you may stray away too far from the original data. Because your model learns something, the distribution of what you output is not the distribution anymore of the training data. And even though you keep the training data in that, you still have a distribution shift over time. There's actually multiple issues now that I think of it. So they say, well, we keep the original data always around. We always do the original data union with whatever comes out of that grow step, right? And that together they call DG for the particular step. So sampling from the model always goes here. Now think about it. So they say, well, we keep this data around, and therefore, we always kind of stay close to the training data. This is kind of a regularizer. Yes, but you filter both data sets, right? This is both. This is DG. You filter both of them by the threshold. So if you do that, you're always going to strike away at least part of that original data. Now, because you train your models using the reward model to produce ever higher rewards, right? Naturally, probably, if we always produce the same amount of data, that means that whatever part is here, I don't know how they call it, will increase in its rewardiness, because it comes from a model that has been trained to produce ever higher reward, while the original data will stay constant, which means in expectation, and it would be nice to confirm that experimentally somehow, but in expectation of the original data, more and more should be slashed away by given the same settings of the filter, or the same percentile of filters, right? Because naturally this data is going to rise in reward and the original data stays constant given the same reward model. More and more of that original data is just gonna not be inside of the filtered version of DG at all. So not only do we train the model to successively conform to the reward model, but we even slash away the data that would prevent it from doing so and stay close to the original data. So it's kind of like a double whammy for that. And only come to think of this right now. So yeah, that might be a reason why too many growth steps aren't ideal, because they observe as well, no matter how good your reward model is, these techniques, they come to what's called reward hacking, where they abuse kind of the differences or the details of the reward model to get very high reward, but to not to like what the humans say is good and what the reward model says is good are kind of they're similar, but they're two different things. And these methods are very good at exploiting details of the reward model so they can get high reward without actually producing higher quality data. It's kind of like an adversarial attack on the reward model. Now, they say online reinforcement learning suffers much more from that than they do, and they claim that in part this is because they keep this original data around, but I'm not exactly sure because they keep kind of slashing it. On the other hand, they also say, more than one or more than two growth steps is probably not sufficient. And again, I wonder, because the main improvement here comes definitely from filtering by the reward model. So what happens if we just use the same original model, like the one from G1, to produce more data and then filter that? Do we really need the new model here to produce that new data? Because it seems like the crucial aspect is going to be the filtering done by the reward model. So couldn't this model here also just produce more data, or is it about diversity of data? Like, I wonder, right? What if I just use the original or the very like theta zero, pi zero or theta zero to produce all of kinds of data, right? I just let it sample, and then I always filter that. And once I have very little data, I just sample some more. Yeah, maybe that's why multiple growth steps are just not super interesting, because could I do this with one model? Or is the fact that I now have a new model that's higher reward somehow, like, for sure I have to sample less, but yeah. Sorry, these are just thoughts that come to mind. So here is the full algorithm outline, and we'll get to the experimental section in a bit, but I have one more gripe first with this. So I don't want to dunk on it too much, right? It's a nice technique, and what it reveals. So the whole paper could actually be renamed. You could rewrite the whole abstract or the whole reasoning behind the paper, which is essentially like, how can we make the best out of the data we have, which seems to be not optimal so far, right? If we can improve our models by like sampling from ourselves and, techniques like this, it necessarily means we don't have the best use of our data figured out while we're training for the first time. That's just that. The second thing is, the paper could just as well be like, scrap all of that, and it's just how, if I have like a really good reward model, how can I make the best use of that? Because that's what the paper does, right? It's like, we have a really good reward model, how can we make the best use of it? Online PPO is probably not as good as what they are doing right here, but that's essentially how I see the paper. Okay, so the full algorithm goes as follows. As you can see, we have all these inputs, and among the inputs is that reward model. Okay, so that's, as I said, the crucial part here that actually makes the whole thing work. In the growth step, we generate the data set by sampling. So this is the original data set, and we union it with this one right here. We take the X from the original data set, and the Y is inferred by our current policy, so by our current, most recently trained model. So we produce a number of data, and then we simply annotate it with the reward model. So during the growth step, we don't do anything. We simply grow our data. And now during the improve step, two steps. First, choose a threshold, right? And then just filter the data by that threshold. Choose a threshold for reward. And they also train value models here. They speak about this, I believe, in the appendix a little bit, but you simply choose a threshold. How you choose that threshold? In one point they say, well, we have a list of thresholds that we try. In other points they say, well, we sort of train a value function and then we decide according to that. I don't know. But while the reward improves on an eval set, optimize the objective. And the objective here is simply the normal language modeling loss multiplied by this F term right here. And the F term is simply the filter by the reward model. So it's just a mathy way of writing I filter my data. You can see right here, the f term is a indicator function that is 1 whenever the reward of the pair is higher than the threshold and is 0 otherwise. So that multiplication, yeah, I get it why they do it, but it's kind of like we haven't had like a full width formula for a while. So quick, throw in some math right here. Good job, good job. Effective mathification. So they train on this new objective on the filter dataset. Now, if you analyze this a little bit, and they do right here, say we have a what they call a probabilistic interpretation. And essentially, they say if you look at the gradient of this loss, the gradient comes from 2 different parts, right? Since our data set consists of 2 different sets, the original data set and this new self-produced data set, we can also split up the loss into 2 different parts. So the loss, essentially, you can see right here, the X is always sampled from the data set. For the part that comes from the original data set, the Y is sampled from the true distribution. So we can also say Y comes from the original data set here. But that's like human annotate, like super oracle labels. It's simply a filtered version of the language modeling loss. So this right here, this is the log likelihood loss that you saw before, the gradient of that, and it's simply filtered by the data. And they claim, okay, this is kind of a regularizer. The second term on the right-hand side, we consider the original data, but we still ensure that it passes the threshold. Intuitively, people choose D according to some possible criteria, yada, 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 yada. The last term is therefore a form of offline policy gradients which prevents it to move too far from the original distribution, which could lead to a model collapse. Okay. Some sort of proximal term. The first part, however, you can see right here, it's the same term. However, the Y now is the one you sampled. Okay? So this, now here, we're in full reinforcement learning mode because we are taking the log likelihood of the input with respect to our own output. Okay? And this is, if you don't know about sort of reinforcement learning policy gradients, you will have X. You will have your policy or your model create Y hat. And then what you do is you just kind of pretend that that's the pair of data points, and you ask what's the loss of this, right? Sorry, I'm explaining this terribly. Maybe I should explain it like this. So what your model will do with X is it will give you a distribution, right? Okay. Now, this is the distribution under the model, so pi of X. So all of these are potential actions, potential Y hats, right? And if, let's just say we take the biggest one, let's say we do greedy sampling. We say, okay, this is my output right here, right? This is the action I want to take. So this is my Y hat. You just pretend that that's the true label. So you just pretend that, you know, that is the actual label. So you take from your own output and you just kind of pretend that's the true label. Okay. And then you train with that. So instead of having the gold label here, right, by the humans, which could be any of these labels, and if it's this one, right, then we were really wrong because this was a smaller logit. But in this case, we just take our own output and we make it into the label. And then we just apply the loss. Now, if we were to just do that, we would just sort of, if this is right, then good, then we make this bar go up next time. But if it's wrong, we also make the bar go up next time, right? So it would not, it's like training on our own data, right? It would not help. So what we need to do is we need to scale it. In classic reinforcement learning, we actually have the reward times the loss with respect to our own data. Now, if the reward is high, that means we want that bar to go up. Because if the reward is high, we've actually done something good, and we want to do it next time more. If the reward is low, we don't want that bar to go up. We actually want all the others to go up. So what usually people do is they replace the reward actually by an advantage function. That's simply their scaled reward. So that's positive if the reward goes high, and it's negative actually if the reward goes low, which means that it would even, if we are wrong, right, if our model is wrong, it would even push that bar down and push all the others up. Right, so that's regular reinforcement learning, and I believe that's what proximal policy optimization does as well. Now what we do here is something very, very similar. So notice that the similarity between what they do, training on their own data, right, and what this reinforcement learning ways do. They are, in a way, also training on their own data, right? Training on data that they have produced, except that they produce it in the moment by outputting the distribution, sampling from it, getting a self-inferred label, and then using that as a training sample in the moment. Whereas this method does it more explicitly. It first produces data by itself, and then it trains against that data. Now, speaking of efficiencies, doesn't that mean essentially we do at least 2 times the forward pass for each sample? Like once when we create the data set and then when we train against it. And in this case right here, we only do 1 time the forward pass because we can then do the backward pass in the moment. So all of the argument of this being more efficient, you have to at least train twice on the same data to make that claim. But I guess they do. You can see here, we don't scale by the reward, but we scale by this filter function. This filter function is, of course, dependent on the reward, but it's not the reward. The filter function is 1 if the reward is high, and the filter function is 0 if the reward is low. Okay? So they even claim this, as you can see right here, similar to online policy gradient, replacing the state action value function when starting in state X and taking sequential actions Y. That is generating synthetic data Y using the policy in our context. So my question is, how much influence does this have? Because in all of these methods, you have to regularize these things somehow. Otherwise, they quickly collapse, right? So, because if you just let them do this RL thing, they will just sort of reward hack and collapse and mode collapse and so on. So you sort of need to treat them very carefully, and you need to make it such that they don't go away from the original objective too much. So you produce your own data here, right? But the original data is actually the true data. So proximal policy optimization and many, many other reinforcement learning techniques, they have regularizers built in to not have them stray away too far. And they don't naturally have a regularizer like this. In fact, they filter down the same data more and more to just the higher quality things. Now they say we decrease the learning rate as that goes on. They also say, well, the right-hand side here is kind of like a regularizer because we keep the original data in there. But as I said, we also filter down that more and more and more. So my question is, and that's not something that's answered in the paper, how much of a regularizer, how much is it actually this thing right here that ultimately does all of this regularization work? The fact that you don't provide a number for the reward or for the advantage, but just a 1 or a 0, like we essentially regularize the coarseness or the quantization of the reward itself. And thus we kind of smooth, because otherwise the loss wants to make the reward go really high, right? And if for one sample it's 0.8 and for another sample it's 0.9, right? That's a difference. So it can make it always go higher. It can make it, even if it's 0.9, it can make it go 0.95 or so. And we know that, this just leads to it could lead to all these reward hacking behaviors where it just focuses on the highest rewards and getting them as high as possible. Whereas here, there's just 1 or 0, right? And the 0, we don't even train on it. So it's just completely regularized and smoothed. My question would be, what if we take this loss and instead of multiplying by the filter function, we just also multiplied by the reward, right? What would happen then? And well, I guess that would result in the online way again. So we would have to find an in between. Like there's an in between of filtering and modeling, multiplying by the reward. Like sort of have a sigmoid in there or something like this. Anyway, this is my question. Sort of the hard breaking and thus the essentially smoothing of the reward of anything that's above the filter to the same level. How much regularization does that contribute? And is that positive or not? So that is essentially the interpretation right here, as you can see. So there is a proximal term over here, which we don't exactly know what influence it has. And there is a filter instead of the reward function as it would be in on-policy learning or in the online reinforcement learning case, which we also don't exactly know what the influence is. But with their techniques, they can reuse the same produced data multiple times by just setting multiple filter settings and focusing on ever higher reward things. And what that results in is reward go up. That's where we were at the beginning. So reward go up. In this case, just for one grow step, so one time they produce more data, as you see, for example, here, G equals 1. And already then, as they do these inner improve step, filtering down more and more, reward goes up. And sure, there is sort of a negative second derivative, but still, it seems to be, goes up pretty well. Now they say right here, on each dataset, we report results with behavior cloning. So this is the original model right here. And what I also find interesting is that they always have this in here, this G equals 1, I equals 0. Now, what that is, according to their own claim, is we do one growth step and we do 0 improvement steps. Now, from an algorithm perspective, this doesn't even make sense, right? Because the optimization happens inside the improve step, which starts from 1. So if I don't do any of that, I shouldn't even be training the model at all. Like the model is never touched according to their own algorithm. But in the text, they kind of describe what they mean. What they mean is we just grow the data set and we don't do any filtering. And as you can see, we already improve. And that is something that I find like a little bit suspect. Like just a little bit. No? No one else does. In fact, they have a comparison down here where, look, so you have this model and you do online RL, like you do online reinforcement learning, a PPO or whatever, with maybe with the same reward model. I hope it's the same reward model. And you get to 71.6. And just by growing your own data and just training language modeling on that grown data, half of which is the original data set, you get more without any filtering. Just by eating your own poop, you just get better result than online RL, which sort of has powered the advances to ChatGPT and so on. This is what I find a little bit suspect about here. And I'm not entirely sure why that would be. I have some imaginations. First, that the RL was not handled super well. Second, that the reward model is just kind of, I don't know, wonky. It's maybe good, but wonky. I don't know. The other thing is that, and they self say in their model section that their models are a bit small. So my question would be, how small, and might that smallness have something to do with, or have they just not trained them really well, right? For some reason, if I can just train on some sample data and get a higher reward than a procedure that is, you know, that is dedicated to maximizing the reward, something's wrong, right? Okay. In any case, if they then do the actual improvement steps and even more growth steps, they get a higher and higher and higher reward. But we are looking on this with a bit of suspicion. Yeah, so they show how if they do multiple growth steps, you can see right here, and then do improvement steps inside of that, then they get even better. It would be cool to see, to have sort of a matrix right here, because they say, well, the growth steps and the improvement steps, they're kind of they're sort of dataset dependent and so on, like how many are optimal, and so you kind of need to babysit. But I would also be interested what happens if I then take this model and just do another growth step, or the I equals 1, and then you know what I mean? Like I always do a growth step. Like what are the trade-offs here? This isn't super well explored. Yeah, but they say for most data sets, more than 2 growth steps aren't really helping too much. Yeah, so that was the paper. They do some other experiments too, and they use human raters. And this is quite interesting. The human raters essentially say, yes, this method is better than the standard language model, that the base language model. However, it's not proportional. So you can see here by how much it is better is not proportional to sort of the improvement that they see on the reward of on the evaluation data sets. So this still means that the reward models and the human ratings, they still are a bit distinct, and it pays to view to that. It's almost an orthogonal direction, but it's interesting that they included that here, which is very cool. So this was the paper. As I said, it's an interesting procedure. Why it works is, so the technical reason why it works is obviously, in my mind, I would have said, is the reward model that just comes from somewhere and is really good, right? And using its power and its knowledge, we sort of distill it into the models using this techniques. However, on the flip side, it seems that if you just do the growth step and use no reward model at all, you get better too, which again, I find I would have said the reward model is the workhorse here. On the other hand, it raises question on just how effectively do we use data, and do we have all of what's there to figure out about training, like just the supervised fine-tuning part. Do we have figured out all there is to figure out? I don't know. I'll leave that to you. Leave me a comment on what you think is going on, and I'll see you around. Bye bye.